Hi, my name is Fabrizio Corda and I'm going to present the paper Real-Time Deformation with Coupled Cages and Skeletons. Skeletons and cages are the two most widely used tools for deformations. Both are composed of handles that allows users to express deformations. Skeletons' handles or bones represent the character joints and are good to deform rigid parts of a body. Cages instead envelop the character they represent and are more suited for local smooth deformations. Skeletons and cages have different expressive powers. For this reason, we propose a novel real-time modeling framework that seamlessly combines skeletons and cages, obtaining a unified structure that merges their capabilities. The major difficulty in combining skeletons and cages stems from the fact that they achieve deformations in dramatically different ways. Skeletons use a relative approach for deformations. In fact, bone rotations are applied to a fixed rest pose, consequently positioning the character vertices. Cages instead use an absolute approach. Any cage uniquely defines a pose. In fact, the character vertices are obtained as a linear combination of the cage handles. Previous attempts to combine skeletons and cages fall short because they are not general enough. They break back compatibility or they aim to different goals rather than create a unified structure. Our main contribution is a deformation system that combines the deformation spaces of skeletons and cages, revealing a much larger deformation space which contains configuration that cannot be achieved using solely a skeleton or a cage. The whole framework is based around four entities: skeleton at current and rest pose and cage at current and rest pose. The user can edit the shape of the rest and current pose character by acting on any of these entities. Anytime an edit occurs, all entities are automatically updated and kept in sync, deforming consequently the character skin. Our framework is composed of three operators that defines how the cage is deformed by the skeleton, how the skeleton influences the cage, and how we can improve the user interaction with the cage. Our framework is a combination of those operators that forms a closed deformation loop. To explain how and why we have defined those operators, we start describing the skeleton skinning pipeline. Here we can observe the classic skeleton skinning diagram, where, starting from a rest pose character and skeleton, we apply edits to the current pose skeleton to obtain the deformation of the current pose character. But what happens when we introduce a cage in this sequence? As we can observe, the skeleton deformation does not influence the cage, rendering the two structures unsynchronized. To create the proper synchronization, we introduce the first operator, the cage updater. Starting from a rest pose, applying a transformation on the current pose skeleton, the character skin will be deformed and, at the same time invoking the cage updater, the current pose cage will be deformed accordingly. More precisely, we seek a cage that generates a skin as close as possible to the deformed character. In this way, editing the current pose skeleton, the current pose cage will be correctly updated and kept in sync with the deformation. Now, we can insert the cage updater into the global pipeline. But what happens if we want to perform an edit on the rest pose cage? In this example, we can observe that, performing this kind of edit on a straight bar, and at the same time bending the bar with the skeleton, we obtain several visual artifacts because cage edits change the center of rotations defined between the skeleton bones and the mesh vertices. To fix this problem, we introduce the skeleton updater operator. Starting from a rest pose and performing an edit on the rest pose cage, this operator will reposition the skeleton bones in a way that preserves the original semantic relation between the skeleton and the skin deformed by the cage, consequently maintaining the correct center of rotation of the skeleton. Here we can observe the same example explained earlier, but with the use of the skeleton updater in the deformation pipeline. As we can see, the deformed shapes look visually correct compared to the same shape obtained without the skeleton updater. Going back to the pipeline scheme, this is how the skeleton updater is used in our framework. But we can note that we still have not addressed what happens if we want to perform deformation over the current pose cage. In this case, we try to compute which rest pose cage allows us to obtain the same deformed current pose cage after the propagation of the skeleton edits. For this reason, we define the last operator, the cage reverser. In details, starting from a rest pose character and applying skeleton deformations, if we deform the current pose cage, this operator will compute a backpropagation of the whole pipeline to obtain the correspondent rest pose cage, keeping the rest pose and the current pose cage coherent with each other. Here we can observe a real-time example of the cage reverser in action. Inserting the cage reverser inside the global pipeline allows us to finalize our framework scheme and observe how all the skinning entities are kept in sync using the defined operators. To test and use our framework, we developed a graphical user interface that allows users to perform mesh deformations and animations using both skeletons and cages. Here we will introduce some examples created using this tool. In this first example, we show that with our framework, artists can explore the space of shapes, selecting the best deformation tool depending on the change they have in mind. In this case, skeletons are used to bend and pose rigid parts like the core of the airplane, whereas cages are used to thicken it or edit the profile of the wings. Interpolating the transformations applied to the skeleton and cage handles, users can also produce computer-generated animations. In this second live demo example, we show that user can download pre-existing animation and enrich them with further effects that are easier to introduce with another deformer. Here, we show a Mixamo character throwing a punch, and the cage was used to inflate its arm. Only one new cage keyframe was generated to enrich the original sequence, inflating the punch, and for this keyframe, we specified the start and end point on the animation time list. We can observe a comparison between the original Mixamo animation and the enriched edited sequence, explicitly showing the skeleton and cage keyframes. In the central part of this video, we can see that visual artifacts will appear if the skeleton and the cage are not kept in sync. In this last example, using another character downloaded from the Mixamo website, we have enriched the animation by inflating and deflating the belly of the soldier as he walks. It is worth noting that all the edits performed by our framework occurs in real time, with negligible overhead to classical skeleton and cage-based deformation workloads. More details about the timing can be found in the full article. In conclusion, observing that skeletons and cages control different aspects of shape modeling, and they are complementary to one another, we propose a real-time modeling framework that seamlessly combines these structures. This combination is made possible by using three operators combined in a specific pipeline, or, according to the necessities, used in a standalone tools. As a result, we operate in a larger deformation space containing poses that are impossible to obtain by acting solely on a skeleton or a cage. To grant reproducibility of our results, we have publicly released the source code of our framework on GitHub. Thanks!